Hi guys, today we're going to be doing a webinar on Cosmos DB, the good, the bad, and the ugly. We're going to be talking about some anti-patterns that commonly occur in Cosmos DB and then how you can either fix or avoid those. So I'm going to be talking about 5 different ones that I've seen crop up in various engagements when I've been working with Cosmos DB. I'm Blaze Stewart. I'm architect at Atmosera in our consulting division, and I'm a Microsoft Azure MVP. If you want to reach out to me, you can always follow me on Twitter and ask me questions there, or you can just email me directly at blaze.stewart@atmosera.com. Either one of those work, and I'll be glad to try to see if I can answer your questions. A little bit about who Atmosera is. Atmosera is a full one-stop shop for all of your Azure needs. We do consulting services, so we come alongside of you and look at your workloads and then help you optimize those for running those on Azure. It could be custom code or applications on Azure, Azure migrations, data on Azure, Azure DevOps, DevOps with Azure using GitHub, whatever it might be. We also do instructor-led training in any of those topics as well. So this could be on demand through WinElect Now or through our instructor-led training, which we come on site and then do instruction that way, or we can do it virtually as well. And then we also have a CSP and MSP business where we manage services on Azure. So we'll take your workloads and we'll manage the infrastructure for you. We'll make sure that everything's up and running. And we have a full staff of people that provide 24/7 support for all things running on Azure for that. We're also a gold partner in just tons of different areas. We're a Microsoft expert MSP and we're GitHub verified partners. We work closely with GitHub to deliver GitHub services, particularly to enterprises and folks that are thinking about using that. And we specialize in delivering services as it relates to code as well as Azure. So we will integrate GitHub and everything GitHub offers with folks that be running workloads on Azure. So that's kind of what we do. Let's go right to the deck and we'll start talking through our content today. So the first pattern I want to talk about is choosing a partitioning scheme that doesn't work for your data. Now, partitioning is one of those things that folks tend to have a little bit of understanding of, but they really don't think about this seriously until usually it's too late. And that's because usually if you just spin up a Cosmos DB cluster and you kind of just take the defaults, everything is going to work fine up to a point. And then the database gets bigger and bigger and bigger. And then all of a sudden you're wondering, why is this thing not performing? You start, ramping up the RUs, you start trying to fix all that stuff. But at the end of the day, it's because you probably have a partitioning scheme that doesn't work for the data that you're going to be using. And there's a couple of different patterns that often crop up. The one that typically ends up happening is folks end up with an unbalanced partitions between their data silos that they have in the context of Cosmos DB. Silos being the partitions that they have in a given container for their data. So this is what we try to avoid generally, because what ends up happening with unbalanced partitions is you'll try to query this data and you'll have one partition that contains most of the data, but you're going to have to go to every partition to query the data. So you got to read all the data out of this partition and every other partition that you might have. And then you got to collate that and send the result set back. And this can take a long time, especially if you have one collection that has all of your data in it. So there's kind of 2 things that we want to think about when we're working with partitioning in Cosmos DB. If we have a small data set, we can typically use a single partition. Now, you don't want to use a single partition for data that's going to grow. If you don't expect your data to grow and it's going to be a relatively small data set, a couple gigs maybe, this is probably fine. And in fact, it's probably encouraged, because this way the query router inside of Cosmos DB is going to send all the queries to a single partition rather than to have to spread that across multiple partitions, and it will operate that particular query inside of a single partition. So if you expect the data to be rather small and you're just going to be basically maintaining that data, either you're just going to be updating existing data, or it's maybe a set of static data that's more supporting other data, such as some kind of dimensional data, that would be one of those things that you could probably use a single partition for and then query against that single partition. If you're going to grow your data, it's just going to grow until you turn the database off in some time in the future and you don't know how large that data is going to get. Then you probably want to use balanced partitioning schemes. Now, there's a couple ways that you can accomplish this. The most optimal way to do this is to think about how your data is going to be queried. Because what you want to be able to do with data is when you query your data, is it's optimal to query that data inside of a single partition if you can. So that's why it's one of the advisable practices for smaller data is to basically have a single partition for that data, and that's fine, rather than having multiple. If you have a large data set, and you're going to have that, millions of records, generally speaking, you want to think about trying to divide that data up into partitions where you can pass in a partition key with each query and then have that query run on a single partition. That way, you're not having to span partitions to query the data. That can be expensive and slow if you have a large query or complex query. So if you can do it in a single partition, it can be rather small in terms of consumption of RUs, but also it's going to be very performant in terms of trying to make that query run rather than having to span across all of the partitions that you have. So one instance of this might be thinking about your data. If my data is organized around, I'd say it's geospatial data. I might want to set up a partition key around some kind of geographic region because I know that the queries are going to be mostly run in that context. So I might say, if I'm saying all my data is more or less geographically going to be located in the United States, the partition key I might use might be something like a zip code, or maybe a municipality or a state, or something like a county. So that would give me a partition key that would more evenly distribute my data across multiple partitions in that case. If it was something like multiple businesses that I have in a software as a service offering that I have, and I have multiple customers, maybe the partition key would be customer data, would be the customer ID in that case. So I would partition it based on the customer, and all of their data gets queried independent of the rest of the people that might be in that same database. So I can use that to run an API against it, and so they log into the API, they're only going to get their data, and most of the queries are going to be run against that. But me on the back end, I might query across all those partitions, but that's not going to be the common thing. That might be only done occasionally, but the lion's share of my queries are going to be distributed across a single instance where I'm going to be serving an API to a single customer. So that might be a good partition key in that case. Regardless, you want to think about how the data is being used to get that data partitioning set up so that you get more balanced partitions in this case. If you're not sure and you're going to have more of a general purpose data set, then you can kind of just use a system generated partition, and that's going to pretty much evenly distribute it by virtue of the data, that the partition key that's automatically assigned to the data. And you can do this just by simply giving the database a partition key, and it will just assign something like a GUID to it, and then you'll basically end up with randomly assigning each record into a given partition that way, and you'll end up with very evenly distributed data, but it's not going to be optimized for any queries in particular. So if you're unsure, that's probably a good default, but if you kind of know what your data is going to be used for, try to find a partition key that's going to optimize your queries so that they run in a single partition. And we'll look at queries more in a minute, but that's kind of the short end of the partitioning story. Now, to kind of look at this, what I did is I created an app. Let me pull this up. And I have an app that I wrote that basically just takes all the syslog data for my firewall on my office. And I basically just upload that data into a Cosmos DB. So I'll show you what the app looks like. This is currently running, and it's just sending data up into Cosmos DB. If I open up this app in Notepad right here, and this is pretty straightforward. So this is just a simple Node.js app that's running as a syslog daemon. And anytime there's a syslog message, basically what it does is it takes this data and does some enrichment on it. And then it uploads it into one of three different collections inside of Cosmos DB. So basically what I have here is a single partition container or collection, a one that I set up as a user partition. This one actually results in an unbalanced partition, and then this one is a system assigned. So this one is basically just using an ID field. So these are the three partitions. Every record is written to all three, and I just did this so I can kind of see what these look like. So inside the context of Cosmos DB, it looks something like this. So this is my database that I have, and these are the three partitions that I have, or three collections that I have right here. And this is my one that has a single partition. If you look at this one's partition key, it's the same for every record because this is a small data set. This is probably the most optimal one for this data, but you can see that I'm using a single partition key for this data. Now, if this was a busy firewall, which mine's not, I would have multiple partitions, but this, for demo purposes, I created a single partition for this, and that's actually probably the best one for this data. The system partition right here, this one is using the ID field. So it's the ID, the partition key and the row key are essentially the same, or the record key right here. Let me, if I can span this out right here. The ID field is both the partition key and the ID field for the given document that I'm storing in this database. So this one right here is the one that's serving as both of them. And for data that doesn't really need a strong partition key, that's probably fine. You can do a single partition key in, and it can also be the same as the ID field. And if you set it up and assign this, it's basically just going to use both, and you can look it up by using the partition key only in this case. You don't have to pass the ID field to look up any record. The partition key becomes the ID field. And this will evenly distribute the data across multiple physical partitions under the hood. And so this is going to be okay for most queries. It's not going to be optimized for most queries, but it'll get me by because it's a general distribution of the data versus one that's going to be more optimized for reading data, as we might see in a single partition for small data sets. Or in this case down here, this one's a user partition where I had the partition key is one that I'm managing basically based on the record type. So the record type is, message type really, right here. And that's the partition key that I'm using. And then it's got an ID for each individual document in this. So this one is, this one still has the single partition key record in there, but that's not what I'm using for my data. You can see here that the message type is the one I'm using for my partition key. And so that is the three different options that I have here. So this one results in kind of some uneven partitions. This one's very evenly distributed, and this one's a single partition, which is optimal for this data because it's actually pretty small. So let's go back to the deck and take a look at another pattern. So we've kind of talked about partitions for a while, and this is a fairly important topic right here. If you're going to be greenfield in Cosmos DB, this is probably something you want to look at very heavily and get your head around what this means and understand your data and the use cases for your data so that you can have a good partitioning scheme that's going to work well for your data. Because this is a lot easier to do before you get into Cosmos DB than after the fact. You can go back and rearrange your data, basically do a data migration from one collection to another, but that takes a while and not recommended that you do that after the fact. But if you can do this before, highly recommend that you get your head around what you're going to be doing for your partitioning scheme, and that's going to work best for your data. And if not, again, you can just take the defaults and kind of let the system evenly distribute the data. So the next thing I want to just talk about is the consistency models. Now, I'm surprised like how often I kind of run into this, because this is usually one of the things that most people kind of understand, because it's kind of one of the things that if you read the literature on Cosmos DB, people talk about this one quite a bit. But at the same time, when I get into the weeds on some of these databases, I start talking to folks and they're like, yeah, I'm doing this one or I'm doing that one. I'm like, okay, why are you doing it? And they make a decision without kind of really understanding the implications of what that's going to imply for their data. So the basic two that are kind of the extremes are eventual consistency and strong consistency. And there's kind of three in the middle right here. The default one is session consistency. Now, basically what that means is a given session that is a single client will pass a session key with every request into the database. And that one basically means that every write is immediately available to every subsequent read, as long as that session key is provided with each request that's made into the database. And that's a good default, especially if you have like an API and you don't have a lot of instances of that API. Say it's maybe like an app service and you'll have a single instance of it, or something like that. This is probably a good default, and that's the reason why. And it's got a balance between consistency and availability and throughput and latency. So you get decent, kind of an average of all those. But one thing I like to consider whenever I'm going into a Cosmos database is this is a default setting. So it's just because it's a good balance. And if you're just not sure, then okay, leave it there. However, one that I like to get folks to think about long and hard is using eventual consistency, because most of the time, at least in my experience, eventual consistency is probably okay for most applications. What that basically means is that once you write data to a database, the read on that data is not going to be immediately available across all of the replicated nodes. So if I'm doing data replication between regions, or even a given region, if I have like some high availability turned on for like zones and stuff, the data is not going to be immediately available for every subsequent read. There's a slight lag between a write and anybody that might read that data. I mean, we're not talking like hours. We're talking usually seconds or milliseconds if it's in a region. It might be seconds if it's in a different region. And for most people, when they think about that, they think, well, the data that I'm writing into my database, I'm not going to be reading this, right after it's written. I'm probably not even going to be reading it, within the next hour or day. It's probably going to be more random, and it's going to be something that I'm not going to have done right away as soon as the record is written. And so a lot of folks are like, yeah, I can live with that in my application. That's fine. And so I say, well, okay, use eventual consistency then, because it's going to be fine for that particular context. Consistent prefix is like eventual consistency. Basically the difference between these two is this one will basically guarantee that any read that I do won't be out of order. So of the writes. So eventual consistency guarantees that the last write will eventually be the one that is out there. But the consistent prefix basically means that I'm never going to be reading something that is out of order from a write. It might skip a few versions of a write of a given record, but I'm always going to get at least one that is going to be more recent than the last time I read that data. So you're not going to get out of order reads in this one. This one you can get out of order reads if you're reading a record like within seconds after it's written, which for most people that's not going to be a problem. So eventual consistency is that eventually you'll get the latest write as available for a read, and on most data sets that's probably fine. And most people think about it, yeah, that's true. So okay, go with eventual. These down here for strong consistency and bounded staleness are for folks that really do need to guarantee that the read is going to be available as soon as it's written. And strong consistency basically guarantees that. That's basically saying, as soon as I write this, everybody that's going to be reading this record will be reading the exact same data that I wrote. And so that is why we say that. The trade-offs, of course, are this doesn't scale. This makes you can't scale across multiple regions. You have longer transaction times, so you don't have so you have higher latency, you have lower throughput that's available, because you basically want to ensure that the latest data that's being written is also available for reads as soon as it's written. Bounded staleness is a little better, because it basically means that it's going to be it's an SLA that says it will be available within this time window. It guarantees the order, and it says it will be available within this given SLA, and that is basically for cross-region replication and that kind of thing. If you want strong consistency in a single region, that basically means that you're going to be bound to a single region. This one gives you the ability to kind of go across regions, but the SLA is that you're not going to get out of date data within a given time window. So there's a given SLA that the writes, your reads might be, a few seconds behind the writes or whatever it might be for this particular SLA right here. But in all that, the trade-off between the strong consistency and the eventual consistency is basically performance. So if you want that stronger consistency, which most people in my experience don't really need, you're going to have high consistency, but your performance is just going to stink because you're not going to get good throughput. You're going to have high latency and their availability is not going to be very good. If you can adopt one of these other more eventual consistency or weaker consistency models, you're going to end up with higher throughput and lower latency on your queries, on your reads. So because this is kind of separating the reads from the writes. And the consistency obviously is low, but this is going to get you better performance on your database. And for most of my experience, this is probably the case that most people are going to be able to live with that context. So I don't really have a good way of showing you this other than just looking at the portal and showing you where to set this. So let me flip back over to that browser window right here. Inside of my database, if I come back over here to default consistency, it's going to set it right here. Now, I like this little graphic here, this graphical presentation right here. It just kind of shows you the nature of the way that reads will happen. This represents your writes right here, and this is your reads. With eventual, it's all out of order, but eventually it'll be consistent. Eventually, the latest data will be what's available for reads. Consistent prefixes basically guarantees that you won't get out of order reads, but it might skip a generation or so, and so you get eventually you'll get the reads will be in order, but you're not going to necessarily get every copy of the data. And session is within the same session in the same region. You'll get the same. The reads and writes are consistent. And then bounded staleness is this one basically is just an SLA. Within a given time window, you'll still get the same reads and writes in the same order. And then strong basically guarantees that everything will be consistent across the board as it's written. So that is one of the trade-offs of this, but this is just not very performant at all. So all that to say is don't prefer this one. Prefer this one if you can, but if that one's not going to work, then think about one of these, one in the middle, but avoid strong consistency if you can, but just because it's really going to kill the performance of your database. I would stick to session if you need it, but try to prefer one of these down here if you can with your given data set. So I'm using eventual on mine, because for my data purposes, that's perfect. So let's go look at the next topic, which is bad query patterns. Now, this is one of those that it's really hard to diagnose this one because it's really hard to see the queries in Cosmos. I wish they got a good way to kind of reverse engineer the queries like you can inside of a SQL Server. You can see what the queries are, and you can look at how the execution plans were set up, and you can kind of diagnose why it's a bad query. This one, you have to kind of look at the query itself and understand what's going on, and look at where your performances might be taking a hit. So you kind of have to play with the queries inside of the portal or inside of the Data Explorer, and see why they're not performing well. And so this is oftentimes one of those things that's not going to crop up until much later. So you write a query, it works great when the data is kind of new and fresh and the data set's kind of small, everything looks fine. But over time, the query becomes increasingly slow and increasingly expensive in terms of consumption. And that's because typically it's using one of these patterns down here, which we'll talk about in a minute. Now, going back to when I was talking about partitions, this relates to that because optimally you want your queries to be able to run a query to run in a single partition, and that's optimal if you can, even in a large database, if you can pass the partition key as part of the query, then the query router isn't going to try to span that query across every partition to find data. It's going to send it to a single partition. It's going to query that single partition. It's going to bring back the data, and you're going to have it available fairly quickly for minimal RUs. And that's one reason you want to set up a partition scheme that's going to be optimal. It's going to be able to best serve the queries that you're going to be running against that data. Now, this is optimal right here. Index queries across partitions is fine if you need to do that. And if you try to avoid this if you can, but it's just typically unavoidable because some queries you need to query across partitions. So you're not going to be passing the partition key with the query. And so the query router is going to go look at every partition that is in your database, and it's going to basically route that query to everyone, and then it's going to collate the results and send the result set back. But it's got to span those partitions when that partition key is not provided as part of the query. So these two are what you want to aim for. Prefer this one if you can. Aim if you can't, then obviously then you try to do a query that is going to be an index query across partitions. Now, when I say index queries, we're basically looking at data where I'm not doing something in the query that's going to have to require the query router to go open up every document, pull the data out, and then do something with it. Everything in Cosmos DB by default is indexed. So if you don't change the index policy, so it's going to take every piece of data, every property, and index it. And that's good because it's building indexes on everything. And you can create custom index policies for more complex queries in Cosmos DB. But this is ultimately where you're going to be using the indexes is whenever you're querying, basically against a single property in your documents. And then you want to probably provide a partition key. If you can, again, across partitions is fine, but you're going to be hitting the indexes more rather than having to go to every document to read the data out of it and do that. And so this is by default what you're going to be doing for most of your queries if you're not doing something that requires you to do an unindexed query across multiple partitions or a single partition. And what an unindexed query basically means is that you're doing something inside of the query that takes a given property and has to do some kind of conversion on it, or it has to do some kind of collation on it, or it has to do something that requires that you read the data, do some kind of data manipulation on it, and then actually do a comparison against some kind of value that it's trying to compare it to. One common practice, and we do it all the time in SQL, is we take a property or a field and we convert it to upper or lower, and then we take the value, convert it to upper lower to lower, and we compare the output from that. And that's basically so we can do case insensitive searches. Well, if you do that, what you're doing is you're taking a value and you're converting it, and it's no longer using an indexed value for the comparison. It's using the values, the stored value for the comparison. And that can get really slow on large data sets because it's literally got to go through every document, open the property, read the property, do the conversion, do the comparison, and then return the result back. And on large documents, that can get really, really slow. And so if you're in a single partition, it's probably not as bad. But if you have to go across partitions, now all of a sudden you have orders of magnitude of compute and latency and time dedicated to a fairly simple query. But you're doing something that requires tons of compute and tons of comparison that isn't against an index. And so this can be orders of magnitude slower and more orders of magnitude more costly than if you would simply just use an indexed query. If you need to do like an example like I just gave, if you need to do case insensitive searches, the way to get around that would just basically store a case insensitive version of the data. So take the property, do a too lower or too upper, store the value, and then that gets indexed. And then you can then search against that case insensitive value that's stored, and then we'll use the index instead of trying to do that case conversion every time you run a new query. And so that ends up getting stored in the database and then indexed, and it's going to be orders of magnitude faster and cheaper if you're going to do something like that. So try to, like I said, if you can, just in terms of queries, try to come up with a partition scheme that's optimal for the way your data is going to be used, and don't do unindexed queries in that data. Use index queries. If you can't come up with a partition scheme that's going to basically ensure that most of your queries are going to be running in a single partition. Across partitions is fine, but that's secondary. So these two are okay. These down here, just avoid them at all costs if you can, because as your data grows, it just becomes more costly, and you'll be like, why is this query so bad? Why am I consuming all these RUs? I don't understand. And many times when I'm getting into the weeds with a customer and looking at their Cosmos, I find queries like this, and it becomes increasingly apparent that we just need to optimize your queries. And if we can do that, we can cut down your costs in Cosmos DB. So let's look at an example of this. I think I can show this somewhat, but it's not going to be easy to see it because it's going to be perform well, because I don't have a lot of data in my database here. But it does show you that it does. Let's do a query against this single partition here, and then I'll look at it against maybe the system partition here. It's because this is so small, it's really not going to matter. Let's query this right here. This is a tag, and if I do, let's get a new query here, and let's do where c.tag equals this. Now this is going to run. It's going to run pretty quickly. It took 12.57 RUs to get that, to run that query. Now, if I do something like this, if I do lower, and let me edit this query right here. If I do lower right here, now I'm doing a case conversion of this right here. And so now it's not going to use the index. And if I do execute query, my query stats, it took a few more RUs because this is such small data. It's just really not going to show the orders of magnitude I'm talking about. But this right here gives me the exact same result. I mean, it's literally the exact same result, but I'm no longer using an index anymore. So if I look at the query stats down here, we can kind of see that it's opening tons of documents and it's reading index hit. It's trying to read indexes, but it's not able to. Instead, it's using the document searches for that, and it's trying to read that document, and it's having to open it up every single time. So let's run this on this one right here with the system partition. I don't think this is going to make any difference here because, again, this is a small data set, but let's just see what happens. And yeah, same RU. So basically, it's because this is such a small data set, it's just really not going to show you what I'm talking about. But at the same time, you can at least see that it's using a few more RUs between a non-index query and one that is an index query. It's because I'm doing that case conversion there, and it's not optimized for that. But in any case, that's how you can see what's going on here. So just try to do that if you can. Try to do everything in a single partition. If you need to go cross partition, that's fine, but make sure that you're using indexes, and then avoid anything that's unindexed, basically, especially if you have to do cross partition queries, and you have to do these kind of conversions like I was just doing. All right, let's move on to the next pattern. Using Cosmos DB for OLAP. Now, OLAP is basically anything that's kind of getting at data analytics. So, Cosmos DB is what we call an OLTP, an online transaction processor, OLTP. And if you see, it's transactional store right here. Cosmos DB is a transactional store, and that's typically oriented around record level operations or row level operations. So it's basically updating data and trying to focus on record level or document level transactions. So it's storing or updating data in that context. Now you can still query that data. That doesn't mean you can't query it, but you're basically selecting data. And that's if you want to basically just filter the data, you're going to filter it. What you try to avoid in an OLTP solution is doing aggregates of data. Aggregates are things like summations, averages, counts, group bys, all that stuff. You can do that in most OLTP solutions. It's just not optimized for it. That's really kind of what you want to avoid with an OLTP database. Now, just because you can do that doesn't mean you should do that. Now, Cosmos DB will let you do some of that that analytic type analysis of the data. it's just not going to be the best experience if you can get away from that and use something that's going to be more optimized for that. And that's where something like Azure Synapse comes in. Now, Azure Synapse is just one solution on Azure that does this, but it does have good tight integration with Cosmos DB using Azure Synapse Link, which is just a feature you can turn on inside your Cosmos DB and then connect it up to an Azure Synapse cluster, and then it just works. There's not a lot of data munging that you have to do because it's doing it behind the scenes for you. So what behind the scenes, what's happening is everything's kind of stored as a row or a record or a document inside of Cosmos, and this only worked for the SQL and Mongo API. If you turn this on, what Cosmos is going to do behind the scenes is it's going to build a column store optimized for analytical queries. And there is a column store database in Cosmos. That's what Cassandra is, and Table API. Both of them are column store data. But if you're using document databases, which is typically what people use Cosmos for, is using Cosmos for that document storage, it's going to try and turn that, basically do a pivot and store everything as a column in that case, so that you can do analytics against it. And they call this an HTAP, which is a hybrid transaction analytics platform. And that is for doing, it's kind of allowing you to do this transactional side over here, as well as this analytics side over here. And so you're trying to optimize for both. And behind the scenes, you're basically just getting two stores of your data. You're getting a column-oriented store and a more document-oriented store. And this is turning it on its side so that it's going to be much more optimized for doing analytics across that data in something like Azure Synapse. Now, of course, you can take Cosmos DB and do data analytics using something else if you want to. This is just one of the built-in mechanisms for it because it's just simple, it's easy to use, and it's kind of an out-of-the-box turnkey solution for doing OLAP instead of OLTP inside of your Cosmos experience. So let me show you what this looks like. It's easy to turn on. It's a fairly new feature in Cosmos. I don't think it's one that's been out for too long, but if I come down here and I use Azure Synapse Link right here, it's just something you turn on, you click, 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 enable, and then it turns it on, come back in 10 minutes or however long it takes to create those data stores. It's basically, if you have existing data, it's going to create the pivots for you. If it's a small data like I have here, it took a matter of seconds. It wasn't very long at all because I just don't have a lot of data. And then it will keep that data up to date once it is in that kind of column-oriented store. And then you take an Azure Synapse cluster and you bolt it up to it, and it looks like this. And I have a query here that I just prepared for it. So now I've got the data store right here, and you kind of come over here, and I've linked the data using Cosmos DB. I just basically created a Cosmos instance, and it's got a special icon. If it is a column-oriented data store, it's got this, it's more column-oriented. It would have something that looks like a document if it was something that was just hitting the document stores directly. But this one has now optimized data for Azure Synapse now. And so you can take this into Azure Synapse, and now I've got optimized data for Azure Synapse, and I can run queries that look like this. Now this is doing some aggregation against it. This is a serverless Synapse cluster, so this is not the most speedy experience, but it does work. And this one is doing it's doing some aggregations now. It's doing a count of the tags, and it's just doing a max in the tag so I can get a single instance of it. And so I'm just counting the tags, and then I'm doing some group by and some sorting, this is all analytics oriented querying. Now I could run the same query. I could adapt this and run it in Cosmos, but it's not optimized for this. This is now. And so now I have a query that's basically giving me a breakdown of everything by message type or tag count, which is the message type. And this is the breakdown. So I have 38,000 records that are just firewall events, things that my firewall blocked, and DHCP, which DHCP requests for devices I have on my network, Nginx, syslog, what have you. All of this is just data, and this is what it looks like when I do that query. So again, analytics queries in Azure Synapse, for the purposes of doing data analytics, and then you let Cosmos do the transactionally oriented data manipulation. So updates and stores and inserts, that kind of stuff. And then filter the data using, filters if you can within a partition, but use something outside of Cosmos for this kind of analytics that you want to do for building this kind of data warehouse stuff that you have right here. So that's the counterpart to the OLTP side of Cosmos DB. So just basically don't use it for OLAP. You don't use Cosmos for OLAP. Use Synapse for OLAP. It's more oriented for that, and that's why you want to use it for that purpose. And let Cosmos do what it's good at, which is OLTP. Now, for the last one I want to talk about in the this particular deck is the SDKs. Now, this isn't so much related to Cosmos as it is how one you might use Cosmos. Now, because Cosmos is often used in conjunction with things like APIs and applications, there is a proper way the SDKs are intended to be used. Now, one of the things that folks typically don't use the SDKs well is they just kind of look at the sample code, they take it, copy and paste it in their application, configure it, say, hey, it works, and then they forget about it. But the sample code is sample code. It's not optimized for the kinds of things that you want to do in a more production workload. So you want to make sure that you're doing something in a more proper way inside of a production-oriented workload so that you don't get problems down the road. Now, the sample code might work for small stuff, and then as you grow, you're like, why is this anomalous behavior? Why is it I'm getting this huge memory footprint? Why is this not honoring my session states? Why am I getting all these problems in my data? And it's largely because folks don't understand how the SDK is working behind the scenes for them. One thing that it does is it maintains connection state and session state for you so that you don't have to manage that. So like, remember going back to those various paradigms that we had for consistency, for different consistency models. One of those was sessions consistency. And so to honor that, you have to have a session, basically a session key passed with each request so that the query router will honor that and will ensure that that is enforced with your consistency model that you have turned on. If you don't pass that key, it's not going to know that it's a query within the same session. And so any gain from a session level, anything gained from session level consistency is lost because you're not using the SDK right. And you might as well go to something more like something like eventual consistency or something like that in order to guarantee that, because you're not getting any kind of guarantee of a session level consistency model, and there's no advantage then. So again, that's one reason you want to use the SDKs properly. The best thing, the advised pattern that every you read the documentation, it's going to say share one database connection for the entire application. Now my voice is getting rough here. You want to share a single database connection across the entire application because if you have to instantiate a new client every time you're requesting, you're losing that session state. You can end up with resource contention. You can end up with thread exhaustion. You can end up with several things like that. And it's really hard to diagnose it because on the surface, it's not the database. It's like, oh, why is my application crashing? And if you start to dig into the weeds on this, you'll find out that, oh, I'm running out of TCP connections. I'm running out of ports. I'm running out of something. The port pool is being exhausted, whatever, because I'm creating all these connections and they're not getting destroyed in the background because by design, it's going to basically spin up some stuff that runs in the background in your application to maintain all of this stuff for the connection states and for the session states and all of these other things that it's doing for you. So you don't have to do that. And so to set up a single connection for the entire application, we basically want to use a singleton pattern or something like that, that it guarantees that I have a single instance of the application for me. And I commonly use a singleton pattern for this, but this would apply to any SDK regardless of what you're doing. Now, this could be Node.js, which is very easy to do with Node.js. You just basically set up something in the root scope that has, the connection and the table, you have the connection in the root scope, everything uses it or something like that. In .NET, you can use a singleton pattern for this. It's very easy to set up using a singleton pattern. I'm going to show you what that looks like, or you could use something else. But in any case, you basically just want something that guarantees you only have a single instance of the client, and then everything uses that single client. So let me show you some example code here of what this might look like. So this is my example code. I have two controllers here that are pretty much the same functionally, but they do things differently. So this is my bad example here. This has got all my parameters for my my application, and my primary keys. Of course, I would store this in a file somewhere or in a key vault or something like that for credentials. But for my demo right here, I'm using this to show you what you don't want to do. So if you copy and paste example code, you're probably going to end up something that looks like this, where it creates a Cosmos client, gets the container, runs a query, executes the query, and gets back the result set and returns it. And then a new query request comes in and rinses and repeats that every single time. In every request right here, I'm getting a new client, and it's instantiating a new client. And then behind the scenes, I've got all this telemetry down here, and I can actually show you what that looks like after I run this, where I have multiple clients that are running in the background. And each one of these clients is trying to maintain a connection state. It's trying to maintain a session state for this given workload right here. And if I do that 100 times, 1,000 times, 1,000,000 times, depending on how busy my API is, I'm going to end up with a lot of clients that aren't being reused. And so I end up with a lot of overhead unnecessarily, and that can cause my memory footprint to swell, all kinds of anomalous behaviors, resource contention, all kinds of bad stuff. And so this is what you kind of want to avoid. Now, a better implementation will look something like this. So this one, I have a singleton class up here. I just basically have a sealed class that basically means that it can't be inherited and so on. I have the same parameters right here, but instead I have a Cosmos client that's a private variable and a container that's a public variable too. This one basically, what this does is I have a private constructor, and then I have a public static instance right here that gets this public lazy loader. I'm just using a lazy loader here, which basically means that the first time I get asked for an instance of this is when it instantiates the connection. It'll create the connection at that point. It stores it, and then every subsequent instance of this will then just pass back the connection right here, the container. And that's really what I want to get so that I can actually run the queries against it. That's really what I'm mostly interested in. And so this one, every time I get the instance right here, I'm basically just going to ask for the container. It's going to use the exact same client. It's going to reuse that over and over and over for every instance, every query that I run against this. And so it's a shared connection. So in this case, I'm just calling my singleton object, going to the instance, and then getting the container. And then that's all I need. And so that's going to recycle that connection every single time. And then I run my query against the single instance of that client. And every time it's going to use the same container, the same instance, and it's going to share the session, and it's not going to mushroom the number of clients that I have created in the background inside of my application. So let me clear the output here, and let's see, clear all. And let's run this bad example right here. We should be able to see a couple of clients that get created, and you'll see like redundancy in the output down here because the database client puts a lot of output in the logs down here. Let's run this, and I should be able to produce a Swagger document quickly if it's loaded. So let's run this bad one right here. Let's try it out using the Swagger. And let's go c.id. Let me get that query that I ran a minute ago from the portal. So let's see, I have my Cosmos right here. Let me get a where clause that I know works. Well, let's get a where clause where I have, let's just get this document right here, where ID equals this right here. And that way I can just, so where c dot ID equals, some value. And let's make sure this query works, which it should. And I'm just going to take this predicate right here and then come back down here into my Swagger document and paste that in right here. and run this, execute. And this is behind the scenes. It's grabbing it. It works. It looks fine. Everything. It looks good. I see my query. I run it again. Hey, look. Hey, it's going to work. And it'll run a third time and a fourth. It looks good. Everything's fine. Hey, my code works. Ship it, right? But behind the scenes, what's going on right here is I have instantiated a lot of different, I'm instantiating new clients every time I connect. And so now I have multiple clients every time I connect to that particular endpoint right here to run my query. And that's what I want to avoid. So let's restart this. Let me clear this out right here. And I'm going to run this using my other one, my better example, if you will. Restart the application and just kind of clean that out real good. And I'm going to use this one right here. And I'm going to paste in that same predicate, except this one, I'm going to run it against the better version of this, so to speak. And now I can execute this, and it actually runs faster because I'm not reinstantiating that client every time. And behind the scenes, my code is running faster because I don't have to instantiate a new instance of the client every time. You can see here that it's kind of spinning up, everything's spinning up. I have a single instance of the client, and now I have the query running instead of having new instance of the client every single time. That's actually a much better approach to doing this. And this is the preferred approach for doing the SDKs. Now, however you do this in your environment, be it Python, Java, Node, JS, or .NET, or if you're just using the APIs in general, if you're just using an HTTP client going against the Cosmos, REST endpoints, same thing applies. You want to make sure that you're using the same client, even if it's an HTTP and you're just calling the REST endpoints. Do that, maintain that connection, so you're not exhausting your thread pools, you're not exhausting your ports, you're not exhausting all of those various things that this is going to end up consuming behind the scenes in that case. So that is the last anti-pattern I want to talk about here. So if you have any questions, please feel free to reach out to me. You can reach out to me right here at the One Mule on Twitter, or just email me. Ask me any questions. I'll try to answer them. I can't get too deep because I have to do my day job, but I'll be glad to help you if I can. And we'll be glad to reach out to me if you have any other questions that you might want answered about Cosmos DB. Hopefully this has been good information for you, and hopefully it'll be something that you can use in your database practice, whatever you're doing with Cosmos DB.